Imagine a theory so powerful that it claims to explain everything from the smallest particles that form the fabric of reality to the most massive structures in the universe. A theory that suggests our familiar three dimensions of space may just be the tip of an invisible iceberg. But what if this theory, despite its mathematical elegance, has never been directly observable? What if the most ambitious idea in physics remains a mystery to this day, even to those who created it? Venturing into the world of string theory, we explore hidden dimensions, unresolved paradoxes, and the ongoing search for the true nature of reality. What secrets does this theory hold, and why, after decades of research, is it still one of the most controversial ideas in physics, history, or science? In the summer of 1968, a quiet revolution began in the hallowed halls of CERN. Gabriel Veneziano, a young theoretical physicist, wrote a paper that, unbeknownst to him, laid the foundations for a theory designed to unravel the very fabric of the universe. Initially, his work was a modest attempt to explain the strong force, the mysterious interaction that holds atomic nuclei together. But soon, this work, entitled Construction of a Crossing Symmetric Reg Behavior Amplitude for Linearly Rising Trajectories, would resonate far beyond its original intent. The scientific community quickly realized the potential hidden in Veneziano's equations. Returning from a short vacation, Veneziano was surprised that his work had already generated considerable interest. It turned out that his model simultaneously solved several complex particle physics questions, which immediately made it a sensation. But at the time, neither Veneziano nor his colleagues realized they were on the cusp of something much bigger, a theory that offered a radically new view of the nature of particles themselves. It took another 5 years before other pioneering theorists, such as Leonard Susskind, Yoichiro Nambu, and Holger Nielsen, revealed deeper implications of Veneziano's model. They began to piece together the idea that elementary particles might not be point-like objects, but tiny vibrating strings. These strings, they argued, could potentially explain the variety of particles observed in nature as different vibrational modes of the same fundamental entity. However, the first steps were fraught with difficulties. The nascent string theory struggled with several inconsistencies, not the least of which was the prediction of massless states, which contradicted the short-range nature of strong interactions. In addition, the theory required the existence of a universe with more spatial dimensions than the three we observe, a concept that, to put it mildly, troubled many physicists at the time. For most of the 1970s, string theory remained on the margins of theoretical physics. The field was dominated by the rapid development of the Standard Model, which successfully explained many particle interactions without requiring additional dimensions or vibrating strings. Many scientists viewed string theory as an elegant but ultimately irrelevant workaround, yet, the story was far from over. The beauty of the mathematics underlying string theory, as well as the persistence of a few dedicated researchers, kept the idea alive. When the success of the Standard Model began to reveal its own limitations, for example, its inability to account for gravity, interest in string theory began to revive. The seeds sown in Veneziano's 1968 paper grew, and by the end of the decade, they had blossomed into a field that would capture the imagination of physicists for generations to come. String theory. A deceptively simple idea. At the most fundamental level, the universe is made up not of point particles, but of tiny, vibrating strings. These strings are unimaginably small, much smaller than anything our current technology can detect. By vibrating, twisting, and folding into specific patterns, these strings give rise to the particles and forces we observe in the universe. Within this framework, the characteristics of each particle, its mass, charge, and spin, are determined by the particular mode of string vibrations. One of the key innovations of string theory is its ability to unify two previously incompatible frameworks, quantum mechanics and general relativity. Quantum mechanics describes the behavior of the very small, atoms and subatomic particles, while general relativity governs the realm of the very large, including stars, galaxies, and the very fabric of spacetime itself. However, the two theories don't fit together well. When physicists try to apply quantum mechanics to the gravitational force, the equations often produce ridiculous results, such as infinite values. String theory offers a potential solution by replacing point particles with strings that can move and interact in ways that avoid these problematic infinities. The elegant merger of the two concepts hints at the possibility that string theory could become the elusive theory of everything, a single theory that could explain all the fundamental forces and particles in the universe. However, the beauty of string theory comes at a price. It requires additional dimensions beyond the usual 3 dimensions of space and 1 of time. According to string theory, the universe consists of 10 dimensions. 6 of which are compactified or curled up so densely that they're indetectable at our current scales. These extra dimensions are crucial because they provide the necessary space for the string oscillations that give rise to the variety of particles and forces we observe. One of the most speculative but fascinating implications of string theory is its prediction of the multiverse, a multitude, perhaps an infinite number of universes that exist parallel to our own. Each of these universes may have different physical laws, depending on how the strings within them vibrate and how extra dimensions are formed. At the heart of string theory is the concept of supersymmetry, a theoretical symmetry that suggests that every known particle has an undiscovered partner, or superpartner. These superpartners can help explain why certain forces, such as electromagnetism and the weak force, behave the way they do. Supersymmetry also plays an important role in string theory because it helps stabilize the theory mathematically and allows gravity to be incorporated into the quantum framework. Supersymmetry plays an important role in string theory because it helps stabilize the theory mathematically and allows gravity to be incorporated into the quantum framework. However, despite its promise, supersymmetry has not been observed in experiments such as those conducted at the Large Hadron Collider. The lack of empirical evidence for both supersymmetry and the extra dimensions predicted by string theory has led some physicists to question whether the theory is a true reflection of reality or just a mathematically elegant construct. Lack of evidence. The bottom line is this: string theory, with its intricate predictions about vibrating strings and extra dimensions, has encountered a serious obstacle: a lack of empirical evidence. Unlike other theories in physics that have been confirmed by observation and experiments, string theory remains virtually untested, existing more as a mathematically elegant framework than as a proven physical reality. One of the most ambitious attempts to find evidence for string theory comes from experiments conducted at the Large Hadron Collider (LHC), the world's most powerful particle accelerator. The LHC was created to study the fundamental nature of the universe by colliding protons at unimaginable speeds. Among the LHC's many goals is to detect evidence of supersymmetry, a crucial component of string theory that predicts the existence of partner particles for all known particles. These superpartners, if found, would provide strong support for string theory. However, despite years of searching, the superpartners were never discovered. The lack of evidence has led to growing skepticism among physicists. Critics argue that string theory may be more of a mathematical construct than a true description of reality. Its reliance on higher dimensions that are inaccessible to modern experiments makes it difficult, if not impossible, to test directly. This has led some to question whether the theory is at all provable, a key criterion for any scientific theory. Nevertheless, one of the most notable discoveries related to the theory occurred a couple of years ago, thanks to calculations made by physicists Pedro Vieira, Andrea Guerrieri, and João Penedones. Using a method known as the bootstrap approach, they calculated a specific number related to the quantum nature of gravity. Bootstrapping involves gaining new knowledge about the world by determining what is consistent with established facts. It's similar to a scientific way of solving problems using tools and knowledge already available. This number, denoted by the Greek letter alpha, represents the size of the first and largest quantum correction to the equations of Einstein's general theory of relativity. Remarkably, their calculated value of in the 10-dimensional supersymmetric universe fully coincided with the predictions of string theory. This coincidence suggests that string theory may indeed reflect some fundamental aspects of quantum gravity. While this result does not confirm that the theory is the definitive version, it strongly suggests that it is still on the right track when it comes to describing the quantum aspects of gravity. In parallel with this experimental work, the development of advanced computational tools has led to significant progress in understanding the potential implications of string theory. Machine learning algorithms have been used to solve the difficult problem of how the extra dimensions of string theory, the Calabi-Yau manifold, translate into the particles and forces we observe. Physicists like Fabian Ruhel and his colleagues used neural networks to approximate the metrics of these manifolds, an important step in determining how they can generate the elementary particles that make up our universe. This approach allowed researchers to calculate the masses of certain particles based on the geometric properties of these manifolds, a significant step forward in connecting the abstract mathematics of string theory to the physical world. However, the debate has become increasingly heated over time. Proponents of the theory point to its mathematical neatness and its ability to provide a potential unification of all forces in nature, something no other theory has managed to do. They argue that the lack of experimental evidence is not a fatal flaw, but rather a reflection of the enormous challenges involved in exploring such fundamental aspects of the universe. Some even suggest that new experimental methods or future advances in technology may eventually uncover the hidden dimensions or particles that string theory predicts. However, this focus on mathematical elegance has its detractors. Critics argue that string theory's reliance on complex and unprovable mathematics pushes it into the realm of speculation rather than empirical science. They warn that the pursuit of this philosophy may divert resources and attention away from other promising areas of research that rely more on observable. This contradiction between mathematical beauty and empirical evidence has led to a broader philosophical question. Is string theory a true physical description of the universe, or is it just a complex mathematical hypothesis? The lack of direct evidence and the difficulty of making testable predictions have led to fears that the theory will never become anything more than an abstract intellectual exercise. While the search for evidence continues, the scientific community remains divided. The promise of string theory as a theory of everything hangs in the balance, and its fate depends on the future of experimental physics and the continued pursuit of a deeper understanding of the cosmos. Black holes. Black holes, some of the most mysterious objects in the universe, represent a boundary where the laws of physics as we know them break down. At their core is a paradox that has puzzled scientists for decades: the information paradox. According to classical physics, when matter falls into a black hole, information about that matter is lost forever, seemingly violating the fundamental laws of quantum mechanics, according to which information must be preserved. String theory offers a compelling scheme that can resolve this paradox. Strings can encode information in a much more complex and subtle way than classical particles. Applied to black holes, the theory suggests that information that enters a black hole is not lost, but is stored in the strings that make up the black hole itself. This intriguing discovery is directly related to Hawking radiation, a theoretical prediction made by Stephen Hawking in 1974. He suggested that black holes are not completely black, but emit radiation due to quantum effects near the event horizon. This radiation, known as Hawking radiation, gradually causes the black hole to lose mass and eventually evaporate completely. However, Hawking's initial calculation showed that this radiation was purely thermal, that is, it did not carry any information about the matter trapped in the black hole. This led to the alarming conclusion that after the black hole evaporates, all information about the objects trapped in it is lost forever, a direct contradiction to the principles of quantum mechanics. String theory offers a possible solution to this problem by suggesting that the radiation emitted by black holes may indeed carry information, albeit in a highly encrypted form. The idea is that the microscopic strings that make up a black hole can encode information about everything that enters it. As the black hole radiates and evaporates, this information slowly returns to the universe through Hawking radiation, preserving the principles of Quantum mechanics, in addition, string theory, suggests that black holes are not just astronomical objects, but also the key to understanding the fundamental nature of the universe. The study of black holes in the context of the theory bridges the gap between the microscopic world of quantum mechanics and the macroscopic world of general relativity. In this sense, black holes serve as laboratories for testing the ideas of string theory and exploring the connections between the micro and macrocosm. The insights gained from studying black holes in the context of string theory may eventually lead to a deeper understanding of the universe's greatest mysteries, bringing us closer to a unified theory of all things, the future. As we move into the future, string theory faces both enormous challenges and unprecedented opportunities. Nevertheless, it's not without its competitors. Competing theories like loop quantum gravity offer alternative explanations for the fundamental nature of the universe. Unlike string theory, which relies on tiny vibrating strings and extra dimensions, loop quantum gravity attempts to quantize space and time itself, proposing that spacetime consists of discrete loops rather than a smooth continuum. These competing concepts are pushing the scientific community to consider a wider range of possibilities in the search for a unified theory. This inevitably raises questions about the very nature of knowledge, the limitations of science, and the boundaries between what is considered empirical science and what can be considered mere mathematical abstraction. Gödel's incompleteness theorem serves as a profound reminder of the limitations inherent in any formal system of knowledge. Gödel showed that in any sufficiently complex system, there are truths that cannot be proved within the system itself. This idea has philosophical implications for string theory. If the search for a complete and self-consistent theory of the universe is subject to the limitations described by Gödel, the question arises, can string theory ever truly realize its ambitious goals? The metaphor of the island of knowledge further emphasizes the limitations of what we can know. As our scientific knowledge expands, so does our awareness of the vast uncharted territories that lie beyond it. String theory, with its reliance on abstract mathematics and higher dimensions, pushes the boundaries of this island, but also emphasizes how much remains beyond our grasp. The more we learn, the more we realize how little we really understand about the universe. This brings us to a key conflict within the scientific community, the tension between empirical science and mathematical theory.